Dear students, in this presentation, we'll discuss few more array operations like searching, sorting, merging. At the end, we will briefly discuss two-dimensional array. The first operations that we discussed in this presentation is bubble sort. It is a process of rearranging the elements. At the end, we'll be getting the list which is in the ascending order or in the descending order. In general, I can say all the elements are rearranged. When compared to the original list, the resultant list will be a modified one, not in terms of the quantity, not in terms of the elements, but in terms of element position. If you consider ascending order of sorting process, the previous elements always with the lower magnitude than the next element. In terms of index, I can write in this way: the previous element always will be the lower magnitude than the next element. The last element will be the maximum of all. The first element is the smallest among all the elements. In this method of sorting, the bigger value will be gradually bubbles to the top of the array like air bubble rising in order, while the small values sink to the bottom of the array. Let us take one array. It seems that everything is fine, that is in the sorted form. Unfortunately, all the elements are in descending order. But we want to sort everything in ascending order. The first element is 5, second element is 4, third element is 3, next element is 2, and the last element is 1. We'll see how the elements are sorted. For this process, we have to iterate many number of times. For that purpose, we have to make use of two loops. One that will indicate number of times that you're going to pick the elements, the biggest element, to place in the proper place, to place in the last position. The second loop, that is for comparing the elements, that indicates how many number of times you have to compare. Here, the number of paths always one less than the total number of elements. Here there are 5 elements. We have to do this operation 4 number of times. In the first pass, that is our number of comparisons. As you can see, right now all the elements are unsorted. First you have to compare 5 and 4, next second and third element, next third and fourth element, next fourth and fifth element. Total number of comparisons required in the first pass is 4. Okay, so once we get the maximum element that we are going to place it in the last place, the list becomes two part. One is sorted part and the other is unsorted part. We will see that in the animation part. Now in the first pass, we are now in the first comparison, comparing 5 and 4. 5 is bigger than 4, so we have to swap. After swapping, 4 and 5 changes their place. As you can see, the bigger element is moving to the next place. In the second comparison, the second element and third element are compared. 5 and 3. 5 is bigger, so we have to move. In the third comparison, 5 and 2 are compared. 5 is bigger, so it has to be interchanged. 5 and 2 has to be interchanged. 5 will go to the next place. It bubbles. Bigger one goes to the actual place, the required place, to the right side here. The next comparison, 1 and 5 are compared. 5 is bigger, so 1 and 5 are interchanged. 5 will take the right position. So this completes 4 comparison. We have completed now first pass. So as you can see, the list has got two parts. One is sorted part, other one is unsorted part. Now we have to consider only the unsorted part. Number of elements in the unsorted part are 4. So 3 comparisons required. First place, second place, and second place, third place, second comparison, third place and fourth place, the last third comparison. We'll see that in this animation. Now we are in the second pass. The first and second element are compared. 5 is bigger, 4 is bigger than 3, so 4 and 3 are swapped each other. 3 gets the first place, 4 gets the second place. The next 4 and 2 are compared, 4 and 2 are swapped, 4 will be moved to the right side. In the next comparison, 4 and 1 are compared, 4 is bigger than 1, 4 will be shifted to the right side, 1 to the left side. Now you can see the sorted part has got 2 element, unsorted has got 3 element. Now we have to consider this part. Now we have completed 2 passes. In the second pass, it took 3 comparison. Now to the third pass. In the third pass, we have to consider only the unsorted part. In the unsorted part, this part, there are 3 elements, 2 comparisons required. If there are n elements, n minus 1 comparison is required. In the third pass, we need to have 2 comparison. 3 and 2 are compared. 3 is bigger, 3 and 2 has to be swapped. So after swapping 2, 3, 1, 4, 5, 4 and 5 are the elements. Next comparison. 3 and 1 are compared. 3 is bigger, swapped with 1. So the list is 1, 3, 4, 5. That completes third pass. Now you can see 3 elements in the sorted part, 2 elements in the unsorted part. We'll go for the next pass, pass number 4. Number of elements in the unsorted part are 2. Number of comparison required in that pass is only 1. 1 and 2 are compared, 2 is bigger, 1 is smaller. They are swapped together. So 1 gets the first place, 2 gets the second place. You can see sorted has got 4 elements, unsorted got only 1 element. So when you got only 1 element, no need to compare. We don't have another element to compare. So that is the end of this. So the relationship here is number of elements if there are n, number of paths, that outer loop should be set to 4 number of times. Why 4? N minus 1. N minus 1 number of times, that is a pass. 0 to n minus 1 number of times you have to repeat. So there are, in this case, there are 4 passes. In each comparison, this is computed as n minus, that is in the first pass, n value minus k minus 1. We'll see what is that value. N is k, that is repeating each time, first comparison, second comparison, like that. Okay, this is the final value. Okay, so in this case, the number of comparison required 4 number of comparison. The next 3, next 2, like that. Okay, algorithm given here. It takes linear array LA, and which is having n number of elements. The equivalent C program is also shown on the right side. We'll be using 3 variables, ptr, k and temp, ptr and k for loops, temp for swapping purpose. LA is single dimension array and n is size. And step number 1, the number of paths from 1 to n minus 1. first pass, second pass, third pass, fourth pass, n k value start from 1 to n minus 1. Okay, this is equivalent C code. In the inner loop, we'll be using PTR. We start from 0. So the final value to reach n minus k minus 1. N minus k minus 1. Okay, this is the stopping condition. PTR value set to 1. PTR value, if it is less than n minus k minus 1, repeat it each time increment value of PTR. For form swapping, if the previous element is bigger than the next element. If previous element is bigger than the next element, swap. Otherwise, skip by incrementing PTR value. By incrementing PTR value, repeat this process. This is about bubble sort algorithm. The next operation that we can perform on array on list is searching. It is the process of finding a particular element in the array. So when we find that element, we'll be returning the position. We say that successful search operation. Till the end also, if that element is not there in the list, we'll be ending up with unsuccessful message. That element is not there in the list. Two different types of searching methods that we used here, that we discuss here. One is linear search, other one is binary search. In case of linear search, after search operation, all the elements will be in the same place. In case of searching, the element will not change the place. In case of linear searching, the array need not be in the sorted form, it can be anything. In the worst case, to find an element which is there in the last place, we have to have that many number of comparisons. That is the worst case. In case of binary search, each time we will be reducing that list to half of the previous. The first one is linear search. As you can see, the elements are not in order. 10, 20, 21, 26 and 45 are the elements. 0th index, first index, second index, third index, fourth index. The item to be searched is 45. Okay, item is there in the set that we know. We'll see that how that is done in the program. Now we are in the pointer position 0th. 10 and 45 are compared. Ten and 45 are compared. They are not equal. They are not equal, but our operation has to be completed. So we'll go to the next position. Increment the pointer. Now pointer pointing to the second element, index 1. 20 and 45 are compared. They are not equal. Proceed further. 21 and 45 are compared. Again, they are not equal. Go to the next element. 76 and 45 are compared. They are not equal. Go to the last element, that is 45. This is the last stopping condition. 45 is equal to 45. 45 is matching with the key element found at position 4. So the location of the element, that is 4. Suppose this is 46. This is 46. What happens? 10 and 46 are compared. They are not matching. 20 and 46 are compared. They are not matching. 21 46 are compared. They are not matching. 76 46 are compared. They are not matching. 45 and 46 are compared. They are not matching. The result will be not found. Location is -1. That indicates that element is not there in the list. Algorithm goes like this. It takes linear array LA, the key element KEY and N as the elements. The right side shows the equivalent C program. It takes three parameters. One is array, one dimensional array, key to be searched, and size of the element, size of the array. We have to repeat it starting from the first index till the last index. If elements are matching, no need to proceed to the next element, return the location. Otherwise, repeat it till you once you reach to the end. If that element is not there in the list, return with -1. This is the equivalency program or the algorithm how that linear search that could be implemented. There are some cases where you'll be given the list itself in the sorted order, like telephone dictionary, the word dictionary, where elements are in order. It can be in the ascending order or it can be in the descending order. Where time of searching is also very important. If the elements are sorted, it is possible to reduce the searching time. The algorithm goes like this. We are taking the mid element. Mid can be obtained by adding the lower index and the higher index average of that. Then you compare mid element with the key element. If that element is matching, can return the position. If the element is not matching, if the element is not matching, like there are two cases. The mid element is bigger than the search key or bigger element is less than the search key. There are two cases. In such case, how to do that one? Suppose this is my array. This is my array. Okay. This is the least element and this is the bigger element. Okay. This is my array 1 having some 5 elements. This is my array. Okay. This is my mid element. Suppose K1 is my key element and mid element say M. Mid element is M. This is lower bound. This is higher bound. Higher index I can say. Okay. L plus H by 2 is mid value. I'm going to compare M and K1. If M is equal to K1, that means you need not compare it again. This is the first case. If the search key is matching that with the mid element, that means element is there, return this M. Case number 1. Case number 2 goes like this. If M is bigger than K1, that means M is the bigger one, but we don't know whether it is there in the list or not. M is bigger than K1, but we don't know K1 is there in the list or not. It might be somewhere here, might be somewhere here, but it is not equal to M. That means we have already compared this M with K1. That K1 is somewhere here. I don't know. For that, I have to consider this part only. Starting from L till 1 less than the mid element, like this. Okay. This is L part. Earlier it was L. This was H. For the next phase, I need not compare this part. I need to compare only this part, but except M. So L in that place only, you change the value of H equal to M minus 1. 1 less than this position. That is, M minus 1 is H value. In that case, no, you have to increment M value. M minus 1 is our new H value. L same. Suppose, this is the second case. Suppose, the third case, if M is less than K1. Now what to do? that k1 is somewhere here. I don't know whether it is there or not. Okay, if there, it might be somewhere here. From here, the next element after m to the last, because we have already compared and failed. Right now we are in the third case, m is less than k1 in this part. So each time you are reducing the list to half of the previous. Earlier it was having say 10 elements. In the next phase we compared 5 elements, like that. So for this purpose, we have to modify the value of L. H is same. In the third case, H is same. H is same. Only L you have to change. L equal to mid plus 1. L equal to mid plus 1. Okay. So M equal to K. If they are equal, stop this process. M greater than K1, change higher value. You have to change H value. In the third case, if m is less than k1, you have to change L value. Okay, this is how binary search algorithm works. Let us take one example. As you can see, list is ordered in ascending order. My search key is 31. To search 31 in the key, first of all I have to find out mid value. This is my L value. This is my H value. 9 plus 0 is 9, divided by 2 is 4.5. We take only integer part, that is 4. This is the mid value. 27 is the mid value. 27 and 31 are compared. They are not same. That means key value is bigger than the mid value. Key value is bigger than the mid value. That means you have to take this part but ignore this element. Mid plus 1 is the next L value. This is L value. This was H. Now also same. L equal to mid plus 1 if key element is bigger than mid element. Okay, next time L value is 5, H value is 9, 9 plus 5 is 14, divided by 2 is 7. For the next time, this is the mid value, 7. 35, in that place 35 is there, 35 and 31 are compared. They are not same. 31 is smaller than 35. That means that element is somewhere here. No need to compare this again. Reduce that mid by 1. 7 minus 1, 6. Earlier L value. New H value. 5 plus 6. 11 by 2 is 5. Then next time 5 and this 5 mid value is 31. This 31 are compared same. So return this location. Return that mid location. Mid value has to be returned. Okay. So element found in that place, return that mid value. This is how binary search algorithm works. Algorithm goes like this. Initially, set up start and end mid value. Initially, you set up start equal to 0, lower index, end equal to n minus 1, higher index. Mid value is start plus end by 2. That you compute it. You have to repeat till this becomes true. Either element is not there or always start should be less than end. Start, while doing that modification, start always should be less than or equal to end, but it should not exceed the value of end. That is a stopping condition. So you can use while loop. Start less than or equal to end, and mid element is not matching that with the key. Then you have to compare. Key is compared with the mid value. If lesser, change higher index. If bigger, change lower index. Change lower index. If same, return. If same, return the key. Return the mid value, saying that element found in the key. If you want to repeat like the left half or the right half, you have to modify the value of mid. That can be modified by adding the latest modified start and end value, taking the average of that. Okay, if the mid value is matching that with the key, return the location value is mid. So at the end, if the element is not there in the list, you are going to return -1. Okay, this is how the binary search algorithm works. The next very simple one, merging. This is a process of joining two arrays. Once you join two arrays, once you merge or concatenate it, the size of the resultant array is sum of size of the original arrays. As you can see, two arrays LA1, LA2, when it is merged, the second array elements are copied after the first elements in the resultant array. First, we have to copy the first array, then you have to place all the elements of second array. The size of this array can see the sum of size of two arrays. The first array is having 7 elements, second array is having 7 elements. The resultant is having 14 elements. That is the result. Now we'll see how that can be coded. We'll be writing a function merge, which is taking following parameters to arrays LA1, LA2, the resultant array LA, size of the first array size 1, size of the second array size 2. The first step is to copy all the elements of array starting from 0th index to the last index to resultant array. Each time you have to increase the position of the resultant array, incrementing the index. Okay. If there are three, I will take a small example here. These are my three elements in the first array and two elements in the second array. Okay. I must have five places here. The first index of the first array is copied to first index. Then I have to increase to 1. In the second place, I have to copy the second element. In the third place, I have to copy the third element of the array 1. Now, after copying, my index of the resultant array is 3. It is waiting. This place is waiting to get the element from the second array. This element is placed here. Then increased. It is 4. That is the way. In this way, elements are copied. Okay, first step done. Second step in the same way, all the elements of second array is copied to that. You can see here, same index in the resultant array is used. Increment, same index variable is used. Okay, that is a common name used for copying the first array or the second array in the resultant array. This is how the program is given. Program can be given, can be designed. The last in this is multidimensional array. As we've seen earlier, it is a brochure. Here, elements are referred with the two indexes, subscript. One will refer the row, say, other one will refer column. This is also known as matrix or a table. An array, if it is A, name of the array is A, two subscripts are required. One will indicate the row, other one will indicate the column. Okay, this is expressed in terms of m cross n, where m is number of rows, n is number of columns. Okay, for example, these values are tabulated in this way: a table, a matrix. These are the three marks obtained for subject 1, for subject 2, subject 3. The row index are 0, 1 and 2, and column index are 1, 2, 3. This is represented like this. Okay, so my array name, say A of 0, comma 0 means this one. A of 01 is 18. A of 02 is 12, like that. In general, if A is my array, J and K are the index, we say that that element exists in jth row and kth column of that array. For two-dimensional array, that can be arranged in column wise or in row wise. We are familiar with row order. row major order. That means if there are m and m cross n matrix or n cross n matrix, can be anything, n cross m. Okay, first you have to fill the elements for the first row. We have to reach to the last column. We are right now in the first row. Reach to the last column, then go to the next row. Again you repeat first row, second row, third. Go to the next row, first column, second column, third column. In this way, elements are arranged. That is called row major. In case of column major, the elements are first filled in the column, then shifting to the next column. Say, if my elements are 1, 2, 3, 4, I have to design a matrix. In case of column major form, the first element will go to the first row, first column. Now we are in the first column only. The 2 has to be placed here. We have completed first column. Go to the next column. The next element will be in the second column. We are in the same column, 3, 4. This is in case of column major. In case of row major, row wise is stored it. First we are in the first row, 1. Go to the next column. Yes, we reach the last column of that row. Go to the next row, 3 and 4. In this way or in this way, elements can be arranged. Okay, so we follow usually row major form, and we have seen this address calculation earlier. The base of the array is base plus w into j minus 1 dot n plus k minus 1. All together, for that w, the size has to be multiplied. As you can see, small difference. How many number of rows you have to skip? How many columns are there in that row? This is that information. How many rows you have to skip? Say for example, I want to get the address of this one. That means I have to skip 2 rows, 2 complete rows. How many columns are there? There are 3 columns are there. That is why m you have to multiply. How many rows you have to skip? Right now I have to find out row 3. 2 rows I have to skip. K minus 1. K is 3. 3 minus 1. 2 rows I have to skip. 2 into number of columns in that row. 3 columns are there. Okay. Then after skipping, now right now we are in the base of that particular row. We are in that row. But I have to reach to this column, second column. For that, how many columns I have to skip? 2 columns I have to skip. From the base, 2 columns I have to skip. Columns j minus 1. Okay, in this case, to go to this one, how many columns I have to skip? First of all, right now we are following now column order, column major order. How many columns? For example, to go to this, I have to skip the first column, I have to skip second column, like that. Okay, that is n. Okay, how many such you have to skip? You have to skip these 2. Then after skipping, now how much you have to skip at the end? That is k minus 1. How many rows you have to skip? That is about address calculation. For this now we'll take index I equal to 2 and j equal to 2. That means I equal to 2, this row, j equal to 2, that is this element. The base address is given, 3018696 is given. All address of the element is also given. As it is integer array, takes 4 bytes. 4 bytes. Now, how many rows you have to skip? 2 rows you have to skip. 2 rows you have to skip. How many columns are there in each row? 4 columns are there in each row. 2 into 4. Then 2 into 4 is that purpose. 2 into 4. 2 rows. 2 rows in each 4 columns. Okay. Then in the last row, interested row, how many columns you have to skip? 2 columns you have to skip. Total of 2 into 4 plus 2. 10. Each requires 4 bytes. Altogether you multiply 4. For that you add it to the base address. As you can see, from the computed value and the actual value, both are matching. This is how the address calculation is used in case of two-dimensional array. With this, I will be ending my presentation on array operation.